So we have a steel guitar string vibrating. It has a little magnet in it. The component of the magnetic field perpendicular to the area of a pickup coil nearby is given by that equation. The circular pickup coil has 30 turns, a radius of 2.7 millimeters, and a resistance of 0.1 ohms. What is the magnitude of the maximum current induced in the coil? So the current induced is due to the induced voltage over the resistance. So there's a voltage that's induced in the coil, and that's because of this changing magnetic field. The magnetic field is changing with time. So this takes us to Faraday's law. The induced voltage is equal to negative N being the number of turns, d phi dt. So it's because the flux is changing that we have an induced voltage. So we need an equation for flux. Now our general equation for flux is the integral of B dot dA. And contrary to popular belief, the integral does not cancel out with the derivative here, because they're not with respect to the same variables. This is the integral with respect to area. This is the derivative with respect to time. So the integral will not cancel with the derivative. But in this case, there's nothing about this magnetic field that suggests it has different values. So at any one moment in time, there's one value of the magnetic field. So that implies the magnetic field is uniform. At any one moment in time, the magnetic field through that little teeny tiny pickup coil is constant. Now it's changing with time, so as you look at different points in time, it will have different values. But the fact that it has one value at any one moment means we can simplify our flux equation to be simply B dotted with A. Now we're also told that this magnetic field equation describes the magnetic field perpendicular to the area. So it's only given us the component of the magnetic field that's passing through the area. So our flux will be simply B times A. And since this is a circular pickup coil, we know the area is pi r squared. We know the radius. So our magnetic flux will be equal to B times pi times r squared. The induced voltage is because this flux is changing. Now the flux is changing because the magnetic field is changing with time. The area is not changing with time, so we can pull the pi and the r squared out, and we need to take the derivative of our flux with respect to time. Sorry, our derivative of the magnetic field with respect to time. Derivative of our magnetic field, the first part, the 50 milliteslas, is a constant. That'll go to 0. Derivative of the sine is cosine. So we still have the 3.2 milliteslas is what that is, times the cosine of that stuff, so 1046 pi t, times the derivative of the inside, which is 1046 pi. So our induced voltage is changing with time. It's not a constant value. It's alternating and changing with time. The equation that describes it is this. We know the number of turns is 30. Times pi times r radius squared. You have to put the 10 to the negative 3 in for the milli there. Radius needs to be in meters. That gives us units of volts. So our voltage is changing with time. We're asked for the magnitude of the maximum current, which will occur when the voltage is maximum. So what's the maximum value of our voltage down there?
1 cosine is equal to 1.
So 1 cosine is equal to 1, so it's the stuff in front. 0.00722 volts. Our resistance is 0.1 ohms. So I ends up being 0.0722 amps, which is also 72.2 milliamps. So that's the maximum induced current. The current is not constant. It will vary according to the cosine function as well, because to get the current function we need to divide the voltage by resistance. So it will also be a cosine function. But the maximum value we can easily find. We could also easily find the value at any point in time, just by plugging in whatever time we're interested in into our function. Any questions? On a side note, I'm very grateful you guys didn't do this. I very commonly see students on a problem like this. I don't remember what end of the coil is. And not over 2R. I see students try to use this equation.
Very good.
Magnetic field of a coil would be N mu naught I over 2R, R being the radius of the coil. Why does this not apply here? Or in terms of at least what we're asking. This certainly would describe the magnetic field of what? Give you a hint. It describes the magnetic field that the coil itself is producing. Which it is. If there's a current in the coil, then it's producing a magnetic field. But this is the magnetic field that the coil itself is producing, which is not this. This magnetic field is due to the little magnet that's in the little guitar string. It's not the same as the magnetic field that the coil itself is producing. And that's why this equation doesn't work in terms of answering this question. If we could, in turn, find the maximum magnetic field that the coil is producing from now knowing the maximum current. But if you want to find the induced voltage or induced current, you want to use Faraday's law is the way to go, which is how you all did it, so that's great.